Muy bien, pues listos, vamos a dar inicio. ¿Qué come? Dona.
Pan dulce.
¿Perdón?
Pan dulce.
¿Perdón? ¿Qué fue?
Un pan dulce, como una concha.
Sí. Ya veo. Bueno. Esta es la mejor forma de darle sabor a tu vida. La clase de geometría que la concha, el pan dulce. Okay, so let's start now. Remember from last time that we defined the Lie algebra for a Lie group. So, but now what we're going to do is we also describe what is the Lie algebra of several Lie groups. So we know what is the Lie algebra of GL. So it is the set of all n by n matrices. We also saw the Lie algebra of SL, which is the set of matrices of trace 0. And finally, we saw the Lie algebra of ON. Can someone remind me what's the Lie algebra of ON?
The antisymmetric matrices?
Right, n by n antisymmetric matrices. Okay, now we described the Lie bracket for a general group, and now let's try to see what it is for this particular group, for GLM. Okay, now let's review some facts that we have seen. So this is an open set in here. So that means that we can use a single chart. So the global coordinates in Euclidean space are used for this manifold. Right, so for any point, a tangent vector looks like this. So xij are the global coordinates of Rn squared. And as you have seen in calculus, for the Euclidean space, we usually identify this notation with the vector notation, right? So it's just an n by n matrix with no other restrictions. And now, in abstract terms or general terms for a Lie algebra, the way that we define the Lie bracket on the Lie algebra was we take two vectors. Each vector induces a unique left invariant vector on the group. And then on that group, we take the usual Lie bracket. And that's how we get the Lie bracket on the Lie algebra. So we have to use left invariant vector fields on the group. Now, so let's try to understand this, okay? Because I want to define the Lie bracket here. But that Lie bracket is given in terms of this. And remember, what is the definition of being left invariant, right? Is this. So the good thing is we computed the differential of this map. And we saw that it is the standard matrix multiplication. When we define the differential of a smooth function, we managed to compute a few of them. And among those examples was left multiplication. Okay, so remember that this is an arbitrary n by n matrix. So instead of looking here, I'm considering the vector like this. G, this is a non-singular matrix n by n. And here is the matrix multiplication. So I obtain an n by n matrix. So that's the differential. And so let's see how, let's try to understand how can we describe or obtain a formula for the left invariant vector field induced by a vector. So I have a vector on the tangent space of the identity that will induce a left invariant vector field, and we have a formula for this given like this. Okay? Right. Now, is this clear for all of you?
Yes.
That's the definition of left invariant for any G in the group. Okay? Right. Now, so that's good. Remember that we would like to describe the Lie bracket on the Lie algebra. So far, we have a description of the left invariant vector field. And now, let's see and try to compute the Lie bracket of two vector fields. Right, so this is our goal. And let's see how to compute it. Okay, so take any two elements of the Lie algebra, and we have the induced left invariant vector fields. By the previous result, the vector at G looks like this. Okay? And now, again, this is when we identify a tangent vector only as a vector, or if you want to use the standard notation from differential geometry, this vector looks like this, right? So this is an n by n matrix. I look at the AJ entry, and that corresponds in the IJ space. Okay. Now, remember that the global coordinates are smooth functions, right? So a vector field, this is a vector field, this is a vector field on the group. If I have a smooth function on the group, I can use the vector field and the function to obtain a new function, right? And that's what we're going to do now. To this vector field, I plug in this function. And what do I get? So if I put the function here, rs, here I'm putting the function rs, and you know what? You remember this, right? Let me use. So this is what we're using in order to get this, right? Is this equality okay for both of you? Remember, I can use either this notation for the vector field at P or this notation. So, is this equality okay for both of you?
I don't quite get it.
Right, okay. I have a vector field that looks like this, right? And well, we have seen how can I, well, here the motivation is a little bit different. But then that's a function. If a vector field is evaluated on a function, I get a smooth function. And now, what is this? So this is F1. Oh, sorry, no, this is incorrect. I want to evaluate in a different function. And now F2, dx2, and so on, right? And remember that the only way that this vector field applied to this function is either 0 or 1. I get the constant function 0 or the constant function 1. And only when they agree do I get a 1, and it corresponds when I have j only. So it says, is this correct?
Yes.
So I'm doing exactly the same. Now, but remember that this is in Rn squared, and my coordinates, instead of having 1, 2, 3 up to n squared, I have 1, 1, 1, 2, 1, 3, and so on. So that's why I have this notation here and this one here. So I'm going to evaluate this vector on one of the coordinate functions, namely XRS. And that's why I only get one entry, and that's when I equals R, J equals S. So this is a matrix, an n by n matrix, and this means that I have the number that lies in the RS entry. Okay? Right. Now, remember that G is a non-singular n by n matrix. A is an arbitrary n by n matrix. If I look at the product, that's the formula for the product, right? On the entry RS. That's just the formula for matrix multiplication. Okay, so this is a function. I have a vector field, a smooth function. I get a function, and it looks like this. Now remember, when I have a vector field and a function, I get a function on the manifold, in this case the group. So G moves in the group, and that will give me a function. As G moves, I'm obtaining different numbers. Okay? But now, this equation can also be written like this. So this, I can put it here. Again, let's say G, G1, G2, Gn. This is the coordinate function. We have used this before, right? That's precisely what I'm using here. This is the coordinate function evaluated at this point on the manifold. I get the RS entry, which is sorry, see, this is a mistake. I'm missing a K, right? Also here. This is the right one. So let's make that correction. So S should be K here. Right? Okay, now sorry for that. Let's see. Okay, now. So I'm rewriting this like this. Note that I'm not evaluating this at G, but if I evaluate it at G, it looks like this. This coordinate function evaluated at G, it will give me G RK, which is here. Okay, so far so good? And this is the formula that we will use, okay? So let me This formula will be useful. Okay, so now we are ready to compute the Lie algebra operation. So remember that A and B are vectors. A tilde and B tilde are the induced left invariant vector fields. So I want to know this at the identity. In that way, I will have the Lie algebra structure. And it happens that this formula is just the commutator of the matrices. AB minus BA. We will compute the whole formula of the Lie bracket of the vector fields. And when we go to the identity, we will obtain this. So now that we're going to prove this, and once that we're done, we have the Lie algebra operation. Great. Any questions before we continue with the proof?
So far, so good.
Okay. Okay, so let's move on then. Again, I'm using the fact that we have global coordinates x, I, j. So this is a vector field. I mean, if you remove this, it will look like this, right? But now, if I look at the vector field at this element, I have to evaluate this, right? So the whole idea is to find the value of this constant. So the problem reduces to find the value of this. Okay, so again, I'm using the same remark that I made earlier. I evaluate this as some particular smooth function, namely the coordinate function xij. So I will get this here. And this vector I'm evaluating at this function. Now, we use the definition of the Lie bracket of vector fields. So is this vector field at the identity evaluated at this function? And now this vector field evaluated at this other function. Now, we know what function is this. Remember? Let's see. Let's see where we computed this. I don't know why did I wrote this. That doesn't seem right. Did I make some mistake here? Yeah, so right. I'm going to use precisely this definition, right? And it's precisely this line. Okay? So ignore this. This is what we computed before, and I'm replacing it here. V tilde evaluated at that function. That's what we have here, right? So, and then the same for this one here. I have it here. Okay. So let's omit that. Now, let's move on. Up to this point, is that clear for all? That equality? Okay. Now, again, we will use the same formula, but now, let's see. I have this vector field applied to the sum of these functions, right? The vector field is linear, so the vector field only applies to this product. Here, you might use the derivation property of the vector field, but remember that this is a constant function. This is the function. Okay, so this is precisely this. A enters. This is a constant, it goes out. So I will get only A tilde applied to this function. Right? Now, do we know what that is? It will be something like this, right? But note that I'm evaluating now here at the identity. Okay? So this G is the identity only. Right? So I will get only ARS when I plug in here the identity. Right? This is right here. If here I put the identity, I will only get ARS once that I evaluate this function. And that's precisely what I get here. AIK. Okay. Take G, the element of the group, the identity in terms of matrix is like this. And you have that function there. Okay, so you get now this expression, but if you look at each term, K is the index of the sum. I and J are fixed, right? And wait, I'm missing something. Or not. Sorry for this, but I'm missing a sum, right? Because this, I mean, this is only and this is the AIJ. So I'm missing one sum. There's one mistake in that computation.
Yes, in the previous line, before that, you just evaluate at one AKJ XIK instead of the whole sum. So that's why you're missing a sum.
Wait, so oops. There, right? Let's see. Let's do it step by step. So this will be the sum. The vector field applied to is linear, and then the constant goes out. Like this, and then minus the other sum. The vector field applied to this function. Okay, now what else? Oh wait, this is K.
We're only looking for the term Cij, right?
Right, yes. This one. So for this one, I apply this function xij. And then here is the definition of the bracket. Here. And then we use the computation that we made before, a vector field applied to that function. So here I have the A, the I, and the J. So this subindex ij is here, I and J. And that comes from this. Rs, R, and S. And then the sum over K. So is this correct? So here I'm just replacing this function by this function here. Now I have to do the same . Let's see. Now, what is this? This is the sum. What is the definition? So this is the sum. Let's put it over S from 1 to n. Okay? And that is A. So I will put A, S. And what is the other one?
K.
Pardon?
K.
Okay. And then times X. X what?
KS.
No, let's see. I have IJ, and the sum term, right? So IJ, and then this. Okay, so here I want to write this. So I put the I. Yeah, it's K, right? Let me put it clearly there. Remember that I made a mistake here. It has to be K and K. Right, so it is, and then what else? IS evaluated at the identity. Is that right? Check it out. In the meantime, I'm going to write the second term. So it should be BSK times X IK of the identity. Is that correct? Okay. Now, let's move on and see if we actually get what we desire. Okay. So the first thing, now tell me what to write. What is here? The sum S equals to 1 up to n of what? You have this function and you are evaluating this function. The variable is S is moving along. And the value of this function is either 0 or 1. When is it equal to 1?
S is I.
Yes. So, again, so all that I get then is A. So everything reduces just to A, IK, sorry. What we had before. So what I'm saying is I only get one term here. Exactly what I had before. Oh, right.
But isn't that right? Because we want only the
Yes.
IJ.
The problem is here. Right. Yes. No. Okay. Good. Well, at least I think it was useful to have this. So I'm sorry about that. That's my mistake here. That's what it was missing, right? It is just the IJ entry. So maybe that's what the comment that you made, Salvador, at the beginning of this. CIJ, maybe you were referring to this. Okay. I didn't get it. Great. Good, good. Okay, so we are done with this. And now let's see what we have proved. So what we have proved is that we know what is the Lie algebra product here. It's just the commutator of the vectors. Okay? And now, of course, it's only on this Lie algebra. But remember that SLN and ON are subgroups. So the tangent space is a subspace. And it will inherit the same Lie bracket. You will get the same Lie bracket on SLN and ON. In fact, more is true. Remember, so the Lie algebra, this is all n by n matrices. And so if you compute this, you will get an n by n matrix. Sure, no problem there. But now, if instead of this, you look at the traceless matrix, sorry, the traceless matrices, and if you do this operation, you will also obtain a traceless matrix. The trace will be 0. And the other case, if you take a non-isometric matrix, 2 of them, and you do the commutator, you will also obtain an anti-symmetric matrix. So I didn't write down that, but that would be the case. Great. So with this, is all that I had planned regarding the algebras, just to express what is the Lie bracket on this Lie algebra and the other two that live there. It's just the standard commutator. Great. So basically here, yes, that's all that I have planned for Lie groups and Lie algebra for the moment. Are there any questions?
I got one above the proposition. Más para arriba, más para arriba. Más. Cuando estamos escribiendo A en X, R, S. Ajá.
Wait, I don't know. So here?
Pues me perdí. No, más abajo se me hace.
Oh, A, okay, it's A. Do you mean this?
Yeah, use the line above that.
Yeah, okay. Here.
Yeah, there. So here we gonna change the order of the multiplication, right? In the terms, G times A, we change it from A times G below.
Right. I mean, so this is correct, right?
Yeah.
Yeah, okay. Here, the order is important because this is matrix product. Here, this is the product of real numbers. The order, it doesn't worry. They commute. The only reason that I changed this was to have here a constant and here a function. But that's right, I commuted both of them just to have the constant function and a function.
All right.
And that's what I wrote. They are equal to this. Here you can commute, but here you cannot commute. You have to be careful.
All right.
But yes, the only reason that it is this expression instead of this one is to have constant times function. That's the only reason that I commute those.
Okay, thank you.
Great. Now, so any other comment? All right. So we have to see differential forms on manifolds. They are fundamental, very important. What I'm going to do, I'm going to do basically more or less a review. Differential forms in Euclidean space. Part of this will be a review. The other part is to show you in some different way how to think about differential forms. And also, I will try to start and again try to emphasize the transition between linear algebra and then differential geometry. So you see, I have differential forms, and let's start by doing some linear algebra here. Again, every vector space is going to be over the rails, finite dimensional, and like that. So take V, any vector space over the rails, and this is something that you know very well, the dual vector space. What is the dimension of this vector space?
The same as the original.
Finite.
The same as this one, right? Both of them have the same dimension. And this is a vector space. The sum of linear function will give you a linear function and a scalar multiplication. Now, we are going to, in some way, give a generalization of this in a different direction, okay? So consider an integer greater than 1, because basically this is what we have at level 1, and now we will do it at level k. So I will look at the set of k linear maps, right? Instead of writing v to the k, I prefer to put it all together. So these are linear maps, and by that we mean linear on each entry. Okay? Again, the set of linear maps is a vector space. Okay? You can add two k-linear maps and obtain a new k-linear map and scalar multiplication. But we don't stop at linear maps. We will require them to be anti-symmetric. So here is where the permutation group enters Sk. Anti-symmetric means that for any k vectors that you put here, and you make a permutation, you will get the same value up to a sign that depends on the permutation. Remember that you have odd permutation and even permutations. So this equation is required, and that's what we mean to be anti-symmetric. Okay? In some cases, this is 1, so we have equality. And in some other cases, we have a -1, and things changes. Okay, so that should hold for any collection of k vectors and any permutation sigma. And so we are looking at k linear maps that are anti-symmetric. The collection of those maps happens to be also a vector space. Sum of function and multiplication by the scalar. Such maps are called alternating k linear maps. And at this point, you can see why do we care k greater than 1. Because when k equals to 1, this is vacuous. There's no, you're not permuting nothing. So for k equals 1, we're not doing anything. This starts to make sense from k equals 2 and on. So we will use this notation for the k alternating linear maps. Okay, capital lambda, k linear maps. And we make the convention that for k equals to 1, we have the dual. And then we go k2, k3, and so on. So each one of them is a vector space. So the convention for k1 is just the dual. Okay. Up to here, any questions? Now, I'm going to give an alternative description of this using the same group, the permutation group, but using the concept of an action of a group on some space. So now I'm going just to consider k linear maps. Okay? I have the set of k linear maps, and I have the permutation group of k letters. Then this group acts on this space. I have an action. So if I take a permutation in a linear map, I'm going to obtain a new k linear map. And the definition of this map is the following. F sigma, if I plug in k vectors, I put the sign of the permutation and then this F. That's how the group, the permutation group, acts on the set of k linear maps. Now, an element here is fixed by the action if this happens for every element of the group, right? That's the definition of a fixed point of the action. So here you can put any element of the group and you obtain the same element on the space. And so if F is a fixed point of the action, means precisely this. In other words, the set of fixed points of this action is precisely the set of fixed, the alternating k-linear maps. So that's an alternative description of the k-linear maps has the fixed point set of this action. So this was more or less trying to review some concepts of actions. Okay, so let's move on with what we have defined. Remember, for k equals 1 is the dual, and then we have all of them, and so on. Right? Do you remember seeing this type of vector spaces? I mean, you must have seen these vector spaces some while ago. Yes or no?
I saw them in the first chapters of the book.
Also, yes, also is on the first chapters of the book. Now, the idea is that this sequence of vector spaces doesn't go forever. It stops. Okay? And in this proposition, so this is a vector space, something that I have seen tell you before, but moreover, the dimension is given by this number, n choose k. That's the dimension of that vector space. Okay, so you can see if k is n, this is a vector space of dimension 1, and this doesn't make sense when k is greater than n. In that case, this vector space is only the zero vector. There's nothing there. So this sequence ends when you reach the dimension of the vector space. So it goes from 1 and so on. Actually, well, I think I will say it below. We also have this, and this is just the scalars. Okay, at level 0. It doesn't depend on the vector space V whatsoever, only on the scalars. Okay, so what I want you to understand is that from one vector space, we constructed many vector space, many of them. The first one you have already seen, the dual, but we constructed more than the dual. And so the dimension here that this ends is what I have here in number 2. I'm putting k equals to 0, so this is the convention. At level 0, the definition is just the field of the vector space. Also, this was our convention for k equals to 1. And from here on, we define those spaces. Using this, you have the dimension of those vector spaces. Okay, so it is symmetric. So this is symmetric, right? Any comments up to this point? So actually, it is possible to give a basis of all of this when you use the wedge product that also appears at the first chapters of the book. Okay, I decided not to review that part, so only this. Now, it is convenient to gather all of the vector spaces into a single one, and we use this notation. Okay? And again, I'm not writing this, you have it there, but this is an algebra. And in fact, I forgot to put the name. Let me put the name of this. This is the exterior algebra. Of the vector space. Okay, so there's a product which is very important, and that's the wedge product. Okay, so again, I'm not going to say nothing about the wedge product. We will use it. It is fundamental also in this aspect of differential geometry. Great. So this is the review up to the linear algebra aspects. Only linear algebra, nothing beyond that. Now I'm going to review what you have seen of differential forms in Euclidean space. So before moving on, are there any questions? Right. So the whole idea is to see differential forms on manifolds, but I want first to review in Euclidean space that you have seen before in multivariable calculus and also on the first chapters of the book. Okay. Also, remember that everything here is smooth. Sometimes I don't write. I just say a one form, a two form, but we always mean that it is a smooth one form or a smooth two form. So here, the general formula for one form is this, where the coefficients are smooth functions, right? Now, I also would like you to remind you what this stands for. Okay, first of all, although we have a D, but let's think of all of this as location, one single object, because later the D would have some meaning, and we will think about it D applied to the function. But in the meantime, there's only one object, which is the xi or j. So this is a derivation or a vector, and this is a vector space. And then the way that we define this has the dual. Okay? So sometimes they call this a covector because it's in the dual. But that's how we should think of this. So this is an element of this vector space, and it is the dual to this one. So far so good? Like this. And let's think about it at a point. Okay? And I really want to stress how we progress from linear algebra to differential geometry. Okay. And basically, this is a vector, but in the same way that we define a vector field, meaning at each point I have a vector, that's what a one form is. At each point, I will get a vector in this vector space, or a covector, right? When you evaluate this at point, this becomes a real number, and this is the covector. So all of that will be a covector, right? So a vector field on Euclidean space is, at each point, I have a vector on the tangent space that corresponds to that point. And that's exactly a one form. At each point, I have a vector, but now in this particular vector space. That's what a one form is. And again, the good thing is in Euclidean space, we have global coordinates, and we can give a formula like this to describe a one form. Okay. And now, again, in Euclidean space, a two form looks like this. There is some smooth function here, and I'm writing this, and this is some short notation. For the wedge product. Okay, but now here, this wedge product is not is the wedge product of forms in Euclidean space, which is induced from the wedge product on vector spaces. Okay, so there you have it. There you have the general formula for a two form on Euclidean space. Or in general, a K form, it will look like this. And using the fact that this is the wedge product and how properties of the wedge product, actually this sum or the indices, you can impose this condition. that they are written in increasing order. And that will give you a formula for a K-form. A general formula in how to write a K-form. Well, and this is exactly what I mentioned before. Right? So these are differential forms in Euclidean space. When we look at the point, we have linear algebra. In one point, I have a different. Hold on, please. Sorry for that. Okay, so we have this now. Up to this point, any questions?
So the forms are mappings from the what was it called? For example, the one form is it's some mapping in the dual, right?
Right, so let's see where. Oh, here, right? Right, so for one forms. So first, the general formula is like this. Let's do it only on R2, X and Y. Okay? So what it means, when you evaluate at one point, you get this. The next thing that I'm going to write, we usually don't do it, it's the same as in vector fields, but I'm going just to make things clear. Like this, right? So at a point, I get a vector in this vector space, in the dual, right? So now this is a number, and this is also a number, okay? So this is what once that you pick a number, basically you are in linear algebra. Any other questions? Moises?
Nope.
Are you sure?
Think so.
Okay. Yeah, so the way to think about all of this is basically when you were studying linear algebra, you have one point, only one, a single point, and above that point you were doing linear algebra. You have your vector space, your dual vector space, the sum of two vector spaces, whatever. Here on manifolds, you replace that point by a manifold. And instead of having now, or instead of having only one vector space, you have many of them for each single point. P1, you have a vector space P1. P2, you have another vector space P2. Those vector spaces are not random, they have something in common. And in order to not just to have a parametric collection of vector spaces, you put calculus and you make things smooth. So whatever meaning you might have when I say, as you vary P in M, you will be moving smoothly above of the vector spaces. And in fact, this is precisely, we will get this in a minute. This is the concept that we have seen of a vector bundle. Okay? So here, you don't care about analysis, calculus, whatsoever, things mean continuous or not. Not important, just linear algebra. But now, on this point of view, you care about, in this case, that things move smoothly. So Salvador, please answer your question.
Yes.
Well, let me know how everything goes. Right, so we have the general description of differential K-form in Euclidean space. So we will not see manifolds until tomorrow. Today, only Euclidean space. So again, I'm going to repeat this. Roughly speaking, a K-differential form is that at every point, you have a vector in this vector space. All right? So that's what differential K for. You see here the K. I'm only talking about Euclidean space and the point. I mean, this is the same thing as a vector field. At each point, I have a vector in TP of n. That was a vector field. In that spirit, it's the same. At each point, a vector, but in a different vector space, not necessarily on the tangent space. Okay. Now, so this is like just the review of everything above. Now, I'm just going to review here some other useful facts that you have seen on differential forms. Right? If this lives in the dual and lives on the vector space, if you evaluate, you get a number. But in this case, it's a one form in a vector field. When you evaluate this, you get a smooth function. And again, this is just to review what I have said before about the duals. Let's do it on R2. And the vector field looks like this, ddx and ddy. Again, any one form takes this form, a function dx, a function dy. So when you evaluate, I'm telling you that you get a function. And what is this? So this with this gives you 1, however, this and this one will give you 0 because it is a dual basis. So there's no alpha 1g, there's only alpha 1f. And the same on the other thing, right? So this function is precisely this function. Like that. Okay, and now I'm making the transition into vector bundles. So the tangent bundle for a manifold is the collection of all of the tangent spaces. It's even more than that, I mean, because we really prove that this is a manifold. We gave an atlas of this, showing that it is a manifold, and the atlas was given in terms of an atlas of the base manifold. But for the moment, I only care that this is the union of all of these tangent spaces. So the whole idea is to replace this vector space, but now by these ones. And we take the union of all of them. That's the definition. It will happen that that is also a smooth manifold. This one here. And as in the case of the tangent bundle, you have the projection map. Okay? So this space, here I'm not saying that, but it will be a smooth manifold. But now, let's look at the following. If I take a point here, what is the pre-image of the projection map? has a set is just precisely this. Okay? So note that for any point that you take on Rn, the preimage is going to be a vector space. It will be a different vector space, but nonetheless, is this vector space. All of them have the same dimension. So in fact, this is precisely a vector bundle. The preimage of every point is a vector space. So this is a vector bundle. Of rank and choose K. Okay, so this is what we have here. When we saw the tangent bundle, maybe at that point it doesn't seem why do we care about tangent bundle, vector bundles. Our only example was the tangent bundle. But now here you can see that you have many vector bundles. So you go from K equals to 0 up to n vector bundles. Okay. And now, that's what I have here actually. So, you see. But now, if you have a vector bundle and you already know what a differential form is, so actually, again, the same way that we saw a vector field, we have a section. A differential form is a section of a particular vector bundle. Okay? Now, remember that for k equals 1, this was defined in a different way. It just was the dual. But also in geometry, we use a different notation. We don't use this notation, we use T star. And that's called the cotangent bundle. So for k equals 1 is different, we don't use this. We have this. And that's the cotangent bundle. Like this. Okay? So above every point, you have the dual of the tangent space. So that's a vector bundle of rank n, because the dimension of the tangent space is precisely n. Right, this vector space has dimension n. So that's the tangent bundle. Any questions up to this point? So again, this is, all of this holds also for manifolds, we will see it, but this is Again, a very different approach of differential forms in Euclidean space. Something that you have seen before, but now from a different point of view. Now, just to finish, I want to talk about the differential. Something that we have seen before, but now in terms of differential forms. So if I have a smooth function, we define this linear map. Remember the differential of P. But now, I think I didn't call it the differential, just the derivative. And it is also called the differential. Given a function, you obtain a one form. The differential. And this is defined by that equation. This is the definition. So you have a one form, you plug in a vector, and what you get is the definition is based on something that we have seen before. Okay? So sometimes instead of writing f star, we will write df. So this is something that we have seen before, and that's our definition of this one here. Right? Again, the same that I mentioned before. Let's think of df has one object. Later, we will see that it's precisely two. It's the function and then some operator, which is the d, applied to the function. In the same way that we have dxj. Let's think that for the moment has only one single object. Okay. So tomorrow we will see differential forms on manifolds and maybe also this operator d. Any questions or comments? And now, so this is very important, the Euclidean case, because in order to define differential forms on manifolds, we will use the charts. So we will have local coordinates. In local coordinates, we can define a differential forms, just like we have done. And in order to have a global form, the only thing that we need to impose is that they agree on the overlap of charts. And that's going to give us a global differential form on a manifold. Okay, so it was a review with a different point of view of differential forms on Euclidean space only. Questions or comments? Right. Now,